All right, so to start out here, let's just establish a notation. This is not anything especially deep in some sense, but it's just a way to notate things that can be of use to us. So we are familiar with what the derivative is. It is a limit. It is a limit of this form, and this form is effectively a way that through limit we can compute the slope of a tangent line. You could run this through examples. In fact, we've done that. So if you let your original function be x squared, well then you could plug in x plus h quantity squared and x squared and go through the computation. You can get yourself whatever the derivative is. Turns out to be 2x. You could run the same computation with something like square root x, something like 1 over x. There's other examples that we've done in class or have shown up in the homework that sort of relate to those situations. But let's just have these as examples. But here's the thing. You know that a derivative is the slope of the tangent line, and you know, in fact, that any slope you could say is an expression of some change in y over some change in x, right? I mean, that's just good old-fashioned slope, rise over run. Now, one way that we sometimes describe change in is using like the Greek letter delta for change in y and change in x, and that's a totally cool way of expressing such a thing. What if we wanted sort of to describe that in other words? Well, the Greek letter delta is corresponding to the English letter d, so sometimes with slope instead of delta y over delta x, we could call this dy over dx. And in fact, the minute that we take that leap, we go from a notation that refers to change in to a notation now that is almost always used in reference to the derivative. So when we talk about the derivative, we could, knowing that it's a limit, fine, we can know that it's a limit, but underneath it all, but we can express that limit as f prime. So if you've got a function f, the derivative is f prime, and what I'm going to say here is that f prime could also be expressed as dy over dx. So dy over dx sort of indicating the geometric nature of the derivative would be just another way to express derivative. So if f of x was x squared, then dy over dx would be 2x. This is, in effect, rephrasing the statement which we've known before in terms of our new notation. And the big difference here is simply that instead of using the notation f prime, we're using the notation dy over dx. Sort of nothing deep or to beat ourselves up over. And yet another way to sort of look at this, and also not to beat ourselves up over, is maybe a different way of interpreting this dy over dx. If you think of dy over dx as a fraction, which it is, you could sort of reinterpret the variables there, and if you, instead of writing dy over dx, wrote d over dx y, note, strange as this may appear, this is another way to express dy over dx, because if you took d over dx times y, you know you can think of y as y over 1, and if you did, multiplying the fractions, you would still get dy over dx. So d over dx of y is another way to express derivative, sort of further supplying us with another notation. But now you say, why would I do such a thing? Here's the idea. The idea is this notation allows you to maybe even more concisely express facts about the derivative. Rather than saying, here's the original function, here's the derivative, here's the original function, here's the derivative, you could use this form to say something more concisely, because you know what y is when referring to any function. Y is just what the function gives you out. In the case of f of x equals x squared, y would be equal to x squared. So we could say, in the context of this problem, d over dx of x squared is 2x. So here would be a way, by example, to see this notation in practice, which is to say the derivative of x squared is 2x. Just as well, by the way, you could say the derivative of square root x is 1 over 2 square root x. But the long story short here is if you park a d over dx in front of a function, what you are in effect saying is you are taking d dx of y, and d over dx of y is really just another way to express dy over dx, which, as we've discussed, is just another way to express f prime, which is the derivative. Now, as I say this is a lot of notation. It may sound like a long path of mental thought to get there, but here's the big takeaway. When you talk about the derivative, you know that it's a limit and you could express it as such. You also could express it more concisely as f prime. You also could express it differently as dy over dx. You also could express that as d over dx of y, which in practice could manifest itself for any particular function as something like d dx of x squared is 2x, or the derivative of square root x is 1 over 2 square root x. But the long story short is there's multiple ways to express the idea of derivative: as a limit, which is its definition, as f prime, which is one way to notate it, as dy over dx, which is another way to notate it, or as d over dx of y, another way to notate it. All of the ideas here are the same, they're just different ways to express it.